Okay, let's do one more probability of a hypergeometric question. So the situation is you deal somebody a bridge hand of 13 cards from a 52 card well shuffled deck. And we are defining X to be the number of aces in that bridge hand. So what is the probability that X equals 5? Well, this is actually a bit of a trick question because the number of aces in a 52 card deck is 4. So the possible values that X can take on are 0, 1, 2, 3, and 4, right? Because in a bridge hand of 13 cards, you can either have 0 aces, 1 ace, 2, 3, or 4. And in fact, you always have to have one of these values. And so the probabilities all sum up to 1 if you add them all up, right? So x equals 2, dot, 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 plus p, x equals 4. These all sum up to 1. And anything else, x equals 5, x equals -1, x equals 6, all of these have a probability of 0. So the answer to this one is 0 because that's not possible. Okay, moving on to part B, the probability that x is greater than 2. So looking at our possible values for x is only greater than 2 when x is equal to 3 or x is equal to 4. So the probability that x is greater than 2 can be rewritten as the probability that x is equal to 3 plus the probability that x is equal to 4. And you could, for each of these, use the hypergeometric formula and calculate that. Would be like a general form, would be that for both of these, and you could sum those up. But I want to talk about a different way to approach a problem like this, and it is called taking the converse. So the probability that x is greater than 2 can also be written as the probability that it's not 0, 1, or 2, right? So the probability that x is greater than 2 is also this probability that x is not 0, 1, or 2, which, because the probabilities all sum to 1, like we said earlier, is equal to 1 minus the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability of x is equal to 2. Now, if we sum all these values up and subtract it from 1, these two will both get you the exact same answer. The reason I bring up this method is a lot of the time with probability questions, one of these two methods will be a lot faster. In this case, they are not that much different. However, in certain situations, calculations like this would be a lot trickier if you had to do one way or the other. So yeah, just wanted to demonstrate that. And let's move on to part C. So the expected number of aces in your bridge hand is equal to n times g over n. N would be the size of the sample, which is 13. Number of good would be 4, because that's the number of aces there are, out of 52, which is the total sample, which is equal to 13 times 4 over 52. And whatever that number is, that is the expected number of ace cards in a random sample of 13 cards. So yeah.